Hey everyone, so we're looking at section 6.2 today, and of course, as you can see, we are going to be talking about applications of the normal distribution. So basically, to be able to use the idea of this normal distribution, your only requirement is going to be that your variable has to be normally or at least approximately normally distributed. And you can actually apply this to a wide variety of applications as long as you fulfill this requirement. So they are saying there are several mathematical tests that can help you determine whether a variable is normally distributed or not. And we'll look at some of them, but of course there are going to be so many that we will not be able to cover all of them. But for now, we are basically going to assume that all the problems that we see in this chapter are going to be normally or at least approximately normally distributed. Okay, so the one thing we are going to need to do is we will need to transform our original variable into the standard normal distribution. So, and you will see this as we go through our example. So we'll need to take our original data value and convert it into a z-score. So you can do that by using this formula over here, or you can look at it in this form. So the x represents our data value, mu of course would be the mean, and sigma of course represents your standard deviation. And then once we transform that variable, then of course we can use our normal distribution table, which is in Appendix A of your textbook, to help us come up with these answers. So let's take a look at this example over here just to see how we can go about doing this process. So they're saying suppose that the scores for a standardized test are normally distributed. So your standardized tests, you can think of examples as your SATs, ACTs, something like that. So they are saying one of these standardized tests has a mean of 100 and a standard deviation of 15. So if these values are given to us, then basically we will need to find out what the z-score is going to be for any data value that we are looking at in this example, and of course transform that into your standard normal distribution value, right? So they are saying when the scores are transformed to z values, your two distributions will coincide. So they're telling us we have a mean of 100 that will be in the center where your standard normal distribution would have a 0. Our standard deviation is 15, so if we keep going up by 15 points, then you would be at standard deviation of +1, +2, and +3. If you start subtracting by 15, then of course you are looking at the standard deviation of -1, -2, and -3. So whenever you are going through these calculations, the one thing you want to remember is to always round your z values to 2 decimal places, and the main reason for that is because in table E, they are using z values being rounded to 2 decimal places. So what's the procedure for this? Of course, we want to start by drawing our normal curve and then shade the area for which they are asking us to find the probability for. The next thing would be taking our data value and converting it to your z value using this formula over here, and then basically find the corresponding area. You can use a table, you can use a calculator, or if you have a software that helps you do that. But of course, in our case, we're mainly going to be using our tables for this. So let's look at this first example over here. They are saying an adult has an average of 5.2 liters of blood. So average, of course, tells us we're looking at our mu value over here. They're saying assume that this variable is normally distributed and has a standard deviation of 0.3. So standard deviation, of course, will give us our sigma value. And they're saying find the percentage of people who have less than 5.4 liters of blood in their system. So as you can see, we start by drawing our normal curve. Our average or mu value is 5.2 liters. They're asking us to find what percentage of people would have less than 5.4 liters of blood in their system. So of course, we're basically trying to find the area of this shaded part over here, right? So the first step we are going to do is find our z value. So we take this data value of 5.4, which is going to be our x value over here. We subtract from our mean, which is 5.2, and then divide that by standard deviation of 0.3. And of course, you will see this comes out to be 0.2 divided by 0.3, which gives you a z value of 0.67. Now, once you have that z value of 0.67, they're actually redrawing that normal curve by now putting 0 as our standard deviation value and 0 as the mean value and 0.67 as the standard deviation value. So basically we know that 5.4 liters of blood is 0.67 standard deviations away from the mean, where your mean is 5.2 liters, right? So now let's go to our table E and see what 0.67 our z-score corresponds to. Okay, so this is positive 0.67. So we look at 0.6 here on the left column, and then for the 0.7 we go to the top row, and this one of course seems to be intersecting at 0.7486. So coming back to our example, you will see that you have an area of 0.7486 corresponding to this z-score. So this area comes out to be 0.7486, or basically 74.86%. So we will say 74.86% of adults will have less than 5.4 liters of blood in their system. So just like we did the calculations in section 6.1, these calculations are going to be very similar to that, but the only difference is the first thing we have to do is take our data value and find its corresponding z-score, right? Because without that, we will not be able to use our table. So that's what we mean by transforming our variables into a standard normal distribution so that we can use our table over here, okay? Now let's look at another example. We're talking about each month an American household generates an average of 28 pounds of newspaper. Again, we're talking about an average here, so that's going to be our mu value. And they're generating 28 pounds of newspaper for garbage or recycling. They're saying assume the variable is approximately normally distributed and the standard deviation is 2 pounds, so that's our sigma value over here. They're saying if a household is selected at random, find the probability that it is generating between 27 to 31 pounds, and for part B, generating more than 30.2 pounds. So let's look at that first one over here. So we know on an average they are generating 28 pounds of newspapers. Now we want to know what is the probability that American households are generating between 27 to 31 pounds of a newspaper, right, for garbage or recycling. So you're going to take each data value, so that's 27 and 31. We plug it into our little formula over here and find the z-scores for both of them. So 27 corresponds to a standard deviation or z-score value of negative 0.5. 31 is corresponding to a z-score or standard deviation value of 1.5. Okay, so let's look at what kind of probabilities we can get from those two z-scores. So we have negative 0.5. So negative 0.5 would be here. And since we don't have any other decimals after that, of course, you're looking at the 0 column over here, which is the first one. So of course, we would be looking at this number over here, which is going to be 0.3085. Okay, so this guy will correspond to 0.3085, and then for our positive 1.5, of course, we'll need to go down here, and again, it's positive 1.5, no more decimals after that, so you're looking at the 0 column. So this, of course, corresponds to 0.9332, so 0.9332. 2. And of course, you will be able to see those values over here in this step 3. And then of course, remember, since we are talking about the shaded area being sandwiched between two different numbers, you have to subtract those probability values, and we would get an area of 0.6247. So this whole shaded area is going to be 0.6247, or as a percent, we would say 62.47% of randomly selected households will generate anywhere from 27 to 31 pounds of newspaper per month. Okay, so this is how you would calculate your probability if you are in between two data values. Okay, now part B here was talking about what if they are generating more than 30.2 pounds of newspaper per month. So again, our mean value is 28. We are saying households are generating more than 30.2 pounds. Of course, we need to find this area in the shaded part. So the first thing we do is take our 30.2, put it into our formula to calculate our z-score. So z-score is coming out to be 1.1. Again, we'll go to our table, look for 1.1, and again, we don't have any more decimals out of that, so we're staying in that first column of 0, 0, which gives us the probability of 0.8643. So you will notice for 1.1 we have 0.8643. However, since this area is to the right of our data value, or to the right of the z-score, remember we have to use 1 minus this probability of 0.8643 to calculate what this area is going to be, and of course that comes out to be 0.1357, or 13.57%. So we will again say the probability that randomly selected households will generate more than 30.2 pounds of newspaper is going to be 13.57%. Okay, so same calculations, like I said, to 6.1, but now we're using them with applications. Now you can also use this idea of the normal distribution calculation to answer questions of how many. So if you were trying to figure out how many households or how many people or anything like that, we could also use the normal distribution for that. So let's take a look at this example over here. They're saying a decibel is a measure of the intensity of sound. So the average number of decimals at a full concert is 120. So this is our mu value. Again, that's the average, right? They're saying assume that the variable is approximately normally distributed and the standard deviation is 6. So that's our sigma value. Now they're saying if 100 concerts are selected, approximately how many will have a decimal level which will be less than 112. Okay, so let's see how this will work out to be. So we are told that the mean number of decimals at a concert is 120. They want to know how many out of those 100 concerts will have a decibel of less than 112. So a decibel of less than 112. So we want to know what this percentage here is going to be, what that, sorry, not percentage, how many concerts will have decibel values of less than 112. So again, take that data value of 112, convert it into your z-score, and since of course this is less than the mean, you will have a negative answer over here. So we've got negative 1.33. So again, looking at our table, we are going to negative 1.3, and then of course we need to go to 0.03 at the top. So this will be right over here. So using that intersection, looks like we are actually coming at 0.0918. Okay, so you can see that right over here. So this here is going to represent 0.0918. But remember, we're not asking for the probability or the percent. We are asking how many concerts out of those 100 will have a decibel of less than 112, a decibel intensity, right? So to find the number of concerts, what we are going to do is take this 0.918 and multiply it by 100. And we're multiplying this by 100 because we selected 100 concerts randomly. Remember, they told us that if 100 concerts are selected, so that's why we are multiplying by 100 over here. So when you multiply 100 with 0.0918, you get a answer of 9.18. Now you can't really have 9.18 concerts, so we're just basically rounding it to the number 9. And so we are saying there are approximately 9 concerts out of 100 that have a decibel output of less than 112. So in this way, you can now calculate how many concerts would satisfy our requirement in this case. Okay? They are saying for problems using percentages, be sure to write the percentage as a decimal before you multiply, and then round the answer to the nearest whole number if necessary. Okay? Alrighty. Now let's see what happens if you are given the percentage or the probability and they are asking you to find the corresponding data value. So they're saying a normal distribution can be used to find the specific data value if you are given the percentages. Okay? So what happens in this case is then if you are given the probability of the percentage and you're finding your data value, we will still use the same formula for our z-score over here, where in this case you will know the z-score, you will know the mean and the standard deviation, but now you are solving for x. So you can rewrite this equation by starting by multiplying by sigma on both sides, so it will get rid of sigma on the right hand side, and then we want to get x by itself, so then you can add this mu to both sides of your equation. So of course your mu will cancel out on the right hand side and you end up getting x equals z times sigma plus mu. So you can actually have the same formula but rewritten so that you can solve it for finding your data value. So it would be this formula right over here. And the procedure table is basically again saying start by drawing your normal curve, shade the desired area that you are given represented by the probability or a proportion or percentile, and then basically find the z value by working backwards from your table that would correspond to that desired area. And we have looked at example of this also when we were looking at 6.1. So let's see how that works in our case of these applications. And then of course step 3 would be to calculate the x value once you know that z value from your table. Okay, so we're talking about police academy qualifications here. They're saying to qualify for a police academy, candidates must score in the top 10% on a general abilities test. So if candidates have a score which is going to be within this top 10%, they will be accepted. If they are anything below that, then of course they will not be accepted. So they're saying assume that the test scores are normally distributed. The test has a mean of 200, so that's our mu value. Standard deviation of 20, so that's sigma. And they're saying find the lowest possible score that would qualify the candidate to be accepted into the academy, right? So again, we start by drawing our normal distribution curve. We know our mean is a score of 200, and then they are telling us we are looking for candidates who score in the top 10%. So that would be this top 10% area that we are interested in. So we want to know, okay, so what should this score on the test be so that they can qualify into this academy, right? Okay, so since this is to the right of our data value, remember the table always tells you what the left or below that data value is. So that's why we're going to work this problem backwards, and you're going to subtract this 10% from our 1. So remember 10% needs to be converted into a decimal, so that would be 0.1, and we're just putting the extra zeros to make it 4 decimal places. So 1 minus 0.01 will of course give you 0.90000. So this area here, which is not shaded, so this part all over here, this is going to be your 90% or the 0.9000. So what you actually have to do is find the data value that would be exactly 0.9000, or at least close enough to it. So let's go to our table, and we're trying to find something close to 90% or 0.9000. Okay, so we are looking at about 89, 80, 89, 97, 90, 9015. So 0.9000 or 90% would fall between these two values. Now, of course, remember you have to use the value which is going to be closer. So 0.8997 is going to be 3 units away from 0.9000, and of course 0.9015 is going to be 15 units away. So that means this number is going to be closer to our 90% approximation. So that comes out to be at 1.28 is what it looks like. So this is going to be 1.28 as our z-score, and you will see we're talking about that right here. So the closest value is 0.8997, which corresponds to a z-score of 1.28. Now, just as a note of reference, here in the parentheses we're talking about, if your area falls exactly halfway between two of the z values, so it's the same distance from both z-scores, then you always go for the larger of the two z values. So they are saying if you look for the area 0.9500, it will fall halfway between 0.9495 and 0.9505. And again, you can verify that right here on your table here. So 0.9500 is going to be halfway between 0.9495 and 0.9505. So in this case, since they are exactly the same distance away from these numbers, you go with the higher number, and so you would end up going with the z-score of 1.65 is what it looks like. So yeah, you would use 1.65 instead of 1.64, and this is only if you're halfway. Now we were closer to 8997, so that's why our z-score is going to be 1.28. Now remember, once you find your z-score, you have to put it back into this formula to find your data value. So our z-score is 1.28, standard deviation is 20, mean is 200, plug all of these in, and you end up getting an answer of 225.6, so round it, and you end up getting 226. So we would say the cutoff score to get into the police academy is going to be 226. So as long as a candidate scores 226 or higher, they will qualify to enter the academy. Okay, so this is another example of how we can use the normal distribution table and calculation to help us find a data value when you know your percentage or your probability. Right, let's look at another example here. We're talking about the systolic blood pressure. So they are saying for a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. We are again saying assume that the blood pressure readings are normally distributed, and the mean systolic blood pressure is 120, so that's our mu. Standard deviation is 8, so that's sigma. And they want to know what is the upper and the lower readings that would qualify people to participate in that study. So remember, they are saying middle 60%. So middle 60%, if this is our mean systolic blood pressure of 120, then basically from that middle, you are going 60%, including the right and the left. So that means from the mean, you are going 30% to the right, and you are going 30% to the left, and we want to know what these data values are going to be. So that's x sub 1 and x sub 2. So if you just think about from the mean, I am going 30% higher, which means that's going to be 0.3000, right? That area, which is going to be the same for this guy also on the left hand side. However, if I think from the mean, so from the middle right here, all the way till the left tail, all of this area is of course going to be a total of, so if you think of this entire area here, this is going to be 50%, right? 0.500. So if I add this 30% to it, it gives me a total area of 80% or 0.800. So that's going to be this blue shaded piece on the left hand side, and then of course this 30% here towards the right of the mean. So together we have 0.8000 as our area. So going to our table over here, you want to find, if you can, 0.8000, and let's see where do we go. So I've got 0.7995 over here, and I've got 0.8023. So I don't have the exact value of 0.8, but I have something close enough. So 0.7995 is going to be 5 units away. 0.8023 is going to be 23 units away. So of course this is our closer value. So you are looking at 0.7995, which corresponds to 0.8 over here and 0.04 here. So that of course becomes a z-score of 0.84. So this is going to be a z-score of 0.84. Now since we know normal distribution curves have symmetry, so if this guy here is positive 0.84, then this guy over here is going to have a z-score of negative 0.84. So you can use that calculation, and of course they're telling you the z value closest to that is 0.84. So taking that 0.84, putting it with our standard deviation and our mean, we can plug it into our formula to get a score of 126.70, which will represent the systolic blood pressure at the higher end. And then using that negative 0.84 for the left hand side, you can again multiply with sigma, add the mean, and you get your lower blood pressure reading as 113.28. So we are saying the middle 60% of the population, so for the research study, the middle 60% will be data values that fall between 113.28 to 126.72. So this x1 value would end up becoming 126.72, and this x2 value is going to be the 113.28. Okay, so again, this is working backwards where you know the percent, but you're trying to figure out what your data values are going to be. Okay, all right, so the last thing I actually want to talk about here in this section is how do we check if our variables are normally distributed or approximately normally distributed or not. So this is where some of those mathematical tests will come into play. But again, we're not getting too much into detail here, but I do want to talk about some things that can help us out in determining if we are looking at a normally distributed variable or not. So they are saying a normally shaped or basically a bell-shaped distribution is only one of the shapes that a distribution can assume, right? Because we know they can be left skewed or negatively skewed, they can be right skewed or positively skewed also. So if you're just looking at a distribution, then how do we know if it's bell-shaped or not? Or if it is even going to be normally distributed or not? So they are saying it is very important, since many statistical methods required that distribution of values be normally or approximately normally shaped. we need to check for normality. So how do we check for normality? They're saying the easiest way is to draw a histogram and check what kind of shape it has. If the histogram is not approximately bell-shaped, then we would say the data is not normally distributed. The other thing we can do is to check for skewness. So to check for skewness, we use the Pearson coefficient of skewness, which we also call as Pearson's index of skewness, and this is the formula for that, to see if our data values are skewed or not. So you take 3 times the quantity x bar, which is of course your mean, subtract the median from it, and divide the whole thing by your standard deviation. So again, remember, x bar is the mean or the average. S is of course your standard deviation, and median of course is median. So they are saying if you do this calculation, your PC, that's the index, if that Pearson's coefficient index is greater than or equal to 1 or less than or equal to -1, then we can basically say that your data is significantly skewed, which means you are either left skewed or right skewed. And if your data is skewed, that means it's not normally distributed. Okay, so this will be the second thing we can do to check. So one is just draw the histogram and check its shape. The second one is looking for this Pearson coefficient of skewness to see if we are seeing data values greater than or equal to 1 or less than or equal to -1. If they are, then our data is skewed. So let's put this to use and see what we have. The other thing they are also saying is that you can check your data for outliers, and we saw this method back in chapter 3. Even if you have 1 or 2 outliers, that can affect the normality of your data values also. Okay, so in that case, again, you can kind of combine all of these techniques and see what kind of data set you have. So this one is telling us in example 6, a survey of 18 high-tech firms showed that the number of days inventory they had on hand. Okay, so this is just showing you from the 18 different high-tech firms the number of days is inventory they had, and they're saying determine if the data are approximately normally distributed. So the first thing, as you can see, is we are constructing a frequency distribution. So that's our little table over here, and then based on that we are drawing our histogram. Now, even though this may not look like a bell-shaped curve, kind of like our normal distribution, you can see we have one peak which is in the center of our histogram over here, and then it's tapering a little bit to the right and it's tapering a little bit to the left. So even though it may not be a perfect symmetric histogram, we can actually say that it is approximately bell-shaped, because again, like I said, right in the middle we have the peak or the highest frequency, or our mode, whatever you want to think about it, is right in the center, and then it starts tapering a little bit off to the side. So we can say just by looking at this that our distribution is approximately normal. Okay, the other thing we can do is check for skewness. So find the mean of your data values, find the median, and find the standard deviation. Once you have all 3 of those values, we can put it in our little Pearson coefficient skewness formula, and you can see this number comes out to be 0.148. So it's a number which is not greater than 1 and it's not less than -1. So because it is staying within this limits of -1 and +1, our distribution is not significantly skewed. So if it's not significantly skewed, again, we can say it is approximately a normal distribution. The next thing you can check for is the outliers. So the first thing we have to do is calculate our quartile 1 and quartile 3. And basically, remember, for the outliers, the idea is your data value cannot be more than 1.5 interquartile range units below Q1, or 1.5 times interquartile range units above Q3. So once you find your Q1 and Q3, find your IQR, or the interquartile range, which is Q3 minus Q1. That gives you 98 minus 45, which is 53. And then you are doing Q1 minus 1.5 times interquartile range, and then that answer comes out to be negative 34.5. And then to find the larger side, you would go with the quartile 3, which is 98, plus 1.5 times 53, which gives you a value of 177.5. So if you just look at your class range over here, or you can go back to your data values right here at the top of the page, we are staying within negative 34.5 and 177.5, because our smallest value is positive 5 and our largest value is positive 158. So we are staying well within these numbers. So obviously in this case we have no outliers. So our histogram is approximately bell-shaped. We have not any significant skewness in our data. We have no outliers. So basically, out of after checking all of those, we can say that our distribution is approximately normally distributed. Okay, so it's definitely going to take a lot of calculation for us to go through this, but once you come up with these values, you can with confidence say that, hey, my data is approximately normally distributed. Okay, one more example over here. So we're talking about the data shown consists of the number of games played each year in the career of Baseball Hall of Fame Bill Mazeroski, and they want to know again if this data is approximately normally distributed. Okay, so we've got the number of games over here. So again, remember, first thing, construct a frequency distribution and a histogram. So here's our frequency distribution, and we've got our histogram over here. Now, just by looking at the histogram, you can definitely see it is not bell-shaped. In fact, it seems to be, so you've got your peak right over here, the highest value, and you can see it's kind of tapering off a little bit more towards the left-hand side. So we can say that the frequency distribution, or even your histogram, shows you that it is somewhat negatively skewed. So just by looking at the histogram, we know we don't have a bell-shaped distribution over here. Now let's check for skewness just to be sure. So we have our mean, median, and standard deviation. Plugging it into our Pearson Coefficient formula, we end up getting a Pearson Coefficient of negative 1.19. So this value, of course, is less than negative 1. And if it's less than negative 1, then again we can say that our distribution is significantly skewed to the left. If it was a number greater than positive 1, then we would have said it's skewed to the right. So since it's less than negative 1, we say it's significantly skewed to the left. Okay, so those two things then work out. Now we check for outliers. So again, we find our Q1 and Q3 values. Find the IQR by subtracting those two numbers. So the IQR comes out to be 59. And then to check for our data values, you take the Q1, which is 96.5, subtract 1.5 times 59, which is the IQR, and we get a score of 8. And then we've got 155.5, which is Q3, add 1.5 times 59, which is our IQR, and that gives us a value of 244. So if you have numbers less than 8 or greater than 244, then we can say we have outliers. But we actually don't have numbers less than 8, because you can see our data values start right at 34, right? Our class is starting at 34, so we don't have numbers smaller than 8. And do we have numbers larger than 244? No, we don't, because we're stopping right at 183. So we don't have numbers larger than 244. So actually there are no outliers here, but definitely by looking at the histogram and looking at the Pearson coefficient, we can definitely conclude that our distribution is somewhat negatively skewed, which means it's not approximately normal, And then, of course, you cannot use your normal distribution calculations on this data set. And then here, they're just actually talking about, you can also check for normality by drawing your normal quantile plots. They're saying quantiles can also be called fractile sometimes, are values that separate your data set into approximately equal groups. You can kind of think of how quartiles and decile works. Quartiles separate our data into 4 approximately equal groups. Deciles will, of course, separate the data set into 10 approximately equal groups. So you can kind of think of your quantile in that same sense. And they're saying a normal quantile plot consists of graphing points using the data values for the x coordinates and the z values, and z values of the quantiles, and then, of course, corresponding to the x values of the y coordinate. So we're not really going to be using the normal quantile plot in this section, but if you are interested in looking at how you can draw these normal quantile plots in your technology step-by-step section at the end of section 6.2, you can actually see how they draw the normal quantile plot if you're interested in that. But basically the idea is, if the points in your quantile plot do not lie approximately in a straight line, then your normality will be rejected. So that's kind of how the quantile plot works. They're saying there are also other methods to check for normality, and some of those are actually shown in your critical thinking challenges at the end of this chapter. You, of course, have the chi-square goodness of fit test that you can use to check for normality. It's in chapter 11. Sometimes you can also use the Kolmogorov or Smirnov test and the Lilliefors test also. So there are, like I said, so many different ways to check for normality, but we are sticking with what we are comfortable with. We know how to do a frequency distribution. We know how to construct a histogram. We can check for skewness based on this formula over here, and then, of course, we can always look for outliers, and all of those can help us determine if we have normally distributed variables or not. Okay, so this was the last thing I wanted to talk about here in section 6.2. Now let's go ahead and take a look at some examples from our textbook. Okay, so the first example we're looking at here is example 4, and this one is talking about the national average SAT score, and that's for the verbal and the math, is 1028. If we assume a normal distribution with standard deviation equals 92, what is the 90th percentile score, and what is the probability that a randomly selected score exceeds 1200? So we have two different questions here. So let's go ahead and see what we can get from that. So we have, not you, there we go. So this is number 4 again. So they're telling us the national average SAT score is 1028. So that's, of course, our mu. They're telling us sigma is 92. Now the first question is asking, what is the 90th percentile score? So that's the first thing we want to find out. Okay, so the 90th percentile score, of course, that tells you that that means 90% of the data values, or 90% of the scores, are going to be below this value. So all of this here will then represent 90% of our score, right? So that means we need to go to our standard normal distribution table and see if we can find the z-score for that 90th percentile, or basically 90%. So looking at our table over here, we need to see what we can get for 0.9000, and let's see, 0.9000. Okay, so again, it looks like 0.900 is going to fall between these values over here. So you've got 0.8997 and we've got 0.9015. So of course .90 will be closer to 0.8997. So we are looking at a z-score of 1.28. Okay, so 0.9000 is actually going to be closer to 0.8997. So that means our z-score is going to be 1.28. Now, of course, we are trying to find what is the data value that corresponds to this z-score of 1.28. So this is where we use this formula where you take the z-score, multiply it with sigma, and add the mu to it. So of course our z-score is 1.28. They're telling us our sigma is 92, and then we are adding the mu value, which is 1028. So if we plug this into our calculator, we actually come up with a score of 1145.76. Let's go ahead and round it up to a whole number. So this will come out to be 1146. So basically we are saying if a student scores at 1146 in their verbal and math on their SAT, they are going to be in the 90th percentile, which means 90% of the test takers will have a score less than 1146. Okay, and the second question was asking us what is the probability that a randomly selected score exceeds 1200. So let's take a look at this one. So again, we'll draw a little normal curve over here. Our mu is going to be in the middle, and that's a value of 1028. And they want to know what's the probability that the score will exceed 1200. So of course, if we are talking about exceeding 1200, then we're looking at this area over here and we're trying to find its probability. So in this case, we of course first need to calculate what the z-score for 1200 will be. So we start by taking our 1200, subtract our mean from it, which is 1028, and then divide the whole thing by 92, and this will end up giving us 172 divided by 92, and as a z-score, this will come out to be 1.87. So once we have our z-score 1.87, then of course we can go to our table and figure out what that probability is going to be. So for 1.87, let's take a look. So 1.8 is right over here, 0.7 is there. So let's see, this will be meeting at 0.9693 over here. So this is going to be equivalent to 0.9693. Now that's of course going to be for everything that is below this x value of 1200. We want to know what is greater than the 1200, right? So remember, for this type of calculation, we will do, so to find the probability that our score is going to be larger than 1200, you will do 1 minus 0.9693, and that will end up giving us an answer of 0.0307. So as a probability, you can leave it like this, or if you want to write this as a percent, that would end up being 3.07%. So we're basically saying, out of all the people who would take the exam and you randomly select a score out of that, there's only a 3% probability that we will find a score that is going to be greater than 1200. So that's kind of what you are looking at here with this example 4. Okay, so our next example is going to be example 16 over here, and here we're talking about the average salary of a male full professor at a public four-year institution offering classes at the doctoral level is $99,685. For a female full professor at the same kind of institution, the salary is $90,333. If the standard deviation for the salaries of both genders is approximately $5,200 and the salaries are normally distributed, then they want us to find the 80th percentile salary for both male and female professors. So let's take a look at this example over here. So we are given the average salary and we are given the standard deviation for both the male and the female professors, and they're asking us to find the salary that goes for the 80th percentile. So if we're talking about 80th percentile, then of course we're basically trying to find this data value here such that you would have 80% of your probability or 80% of the area which would fall below this X value, right? So that's the same thing they want us to do for both male and female professors. So of course the first thing would be is to go to our standard normal distribution table and see what our z-score would be corresponding to this 80% or 0.8000. So again, we're back over here and we're looking for 0.8000, and looks like the closest thing we are going to get to is right here at 0.7995, because 0.8023 is going to be farther away. So the closest value to 0.8000 is going to be 0.7995. That has a z-score of 0.84. So for 0.8000, our closest value is 0.7995, which corresponds to the z-score of 0.84. And of course, this will be true for the female professors as well. So same z-score over here. And now that we have our z-score, we just need to calculate our x value. Okay, so to find our x value, of course, we are going to be using the same formula we saw before. So this is z times sigma plus mu. So we need to do this for each of our groups here, for the male and the female full professors. So let's start with the male professor. So our z-score is, of course, 0.84. Remember, your sigma is 5,200. And the mean value here is going to be 99,685. So if you put this in your calculator, you should get a x value of $104,053. So at the 80th percentile, the salary for the professors is going to be at $104,053. Okay, now let's see for the female professors. Again, our z-score is 0.84. Sigma was the same as 5,200, but the mean value here is $90,330. So again, when we calculate this, we should get a total value of $94,698. And again, this is for the 80th percentile for full professors who are females. And you can see there's a pretty wide gap here between the male professor's income and the female professor's income. So you can see, again, you know, we talk about the gap between how men and women are paid. You can kind of see that in this example also. But again, you have your 80th percentile, which was given to us, and then based on that we came up with our data value. Okay, so this was example number 16. Okay, so the next example we are looking at is number 42. This one is talking about the data shown represent the number of runs made each year during Bill Mazeroski's career, and they want us to check this for normality. So the first thing I would recommend you guys to do is go ahead and arrange this in order from the smallest to the largest data values. Okay, so let's go ahead and take a look at this guy over here. So I've actually already gone ahead and arranged this from the smallest to the largest data value. And then you will notice I actually also went ahead and calculated my class width, because the first thing we are doing is constructing our frequency distribution, and we're going to draw our histogram. So class width would of course be taking the largest data value, subtracting the smallest one from it. So 71 minus 3 gives us 68. And then I guess I'm going to break this down into 5 classes. Just go with the minimum number of classes here, so divide by 5, and we get a value of 13.6, which tells us our class width should be 14. And then based on that size of class width 14, I started with our lowest data value of 3, and you can see I went ahead and created my 5 classes, and then I've got my class boundaries. And then once I had my class boundaries, I went ahead and got my frequencies taken care of. And now that we have our frequency distribution done, we can of course go ahead and draw our histogram over here. All right, so we've got our x-axis. As you can see, we have the class boundaries on the x-axis. We have our frequency values on the y-axis, which represent our years. Okay, so basically you can see for the first class, we have a frequency of 2. So when we draw our histogram, and you can kind of see this is all freehand, so it's not going to be very accurate, but at least it'll give us an idea. For the second class, we have a frequency of 3. So we are looking at something like this. Let's see, we fall back to a frequency of 2 for the next bar. So let's see, frequency of 2, and then we have frequency of 5 for the last 2 classes. And this will end up giving us something like this. Okay, this is really terrible, but hopefully you at least get an idea of at least a general idea of what that histogram is going to look like. So as you can see, obviously this is not a bell-shaped or somewhat symmetrical distribution over here. In fact, it looks like we have the concentration of our data values on the right-hand side, and it's tapering a little bit towards the left-hand side. So I would actually say that this distribution is negatively skewed. Because of course you can see it's kind of forming a little bit of that tapering tail towards the left-hand side. Okay, so that's our histogram and our frequency polygon. Now the next thing we want to check for is skewness. So to check for the skewness, we use our Pearson coefficient. So that formula is 3 times the mean minus the median divided by our standard deviation. So I've already calculated our mean, which will come out to be 45.2. So basically, remember, for the mean, you would add all the data values and divide by the total number of data values. So that's the mean. The median will be the centermost value, and that actually comes out to be this number 52 over here. So this is our median. So median is 52. And then standard deviation will take a little bit of calculation, but again, I went ahead and did the calculation ahead of time. So the standard deviation is coming out to be approximately 20.6. Okay, so once we get these values calculated, and you can look at the formula for standard deviation back in chapter 3 if you are having a hard time recalling it. Okay, so we have 3 times 45.2 minus 52, and then this whole thing divided by 20.6. So when we do our calculation, you get an approximate value of negative 0.8. 0.99. Now this number, as you can see, is very close to -1, right? And remember what we said, if our Pearson coefficient index of skewness was going to be greater than or equal to +1 or less than or equal to -1, then we would say that we had a significant skewness. So since this number is basically pretty close to -1, we can say again that our distribution has a significant skewness towards the left, right? So we will again say the distribution is showing significant, oops, that was wrong. Significant skewness to the left, which would again basically mean negatively skewed. Okay. Now the next thing we want to check for is of course the outliers. Okay, so to calculate our outliers, we do Q1 minus 1.5 times the interquartile range, and then of course to find the higher ones, you do Q3 plus 1.5 times the interquartile range. So our Q1 quartile 1 value comes out to be 29.5. Quartile 3 will come out to be 60.5, and then of course when you subtract these two values you get the interquartile range, which will come out to be 31. So when we plug these values in, we get 29.5 minus 1.5 times 31, and then on this side you will have 60.5 plus 1.5 times 31. So when we solve for these values, we end up getting -17 and +107. So now if you have any data values that are less than -17 or greater than 107, we would say that those would be our outliers, right? But of course you can see our smallest data value was 3 and the largest data value was 71. So this is actually telling us that we have no outliers for this data set. So no outliers, but looking at our Pearson coefficient, we know there's a significant amount of skewness to the left, and then just by looking at our histogram, we also knew that it was skewing towards the left, or it was basically negatively skewed. So in this case, we would say the distribution is not normal. It is negatively skewed. Okay, so hopefully this kind of shows you what the steps are involved in trying to check for normality. So again, these are the examples I wanted us to look at. Now I'll have a few more examples when we talk about this section in class, but look over your notes, look over the video, and let me know if you guys have any questions. Okay, so be careful, be safe, have a great day guys, and I will see you in class. Bye bye.